All right, let's take a look at how to take an oxidation reduction reaction and write the two balanced half reactions for that oxidation reduction reaction. So the first thing we want to do is split apart the things that are aqueous here so we can see if there are any spectator ions. So here we have copper 2 nitrate. This is aqueous, so that means in this solution it would actually exist as copper 2 plus 2 NO3 minuses. Right, we're just splitting that into the cation and the anion, and then we have zinc, which is a solid, and then we end up with copper, that's a solid, and then we're going to split the zinc nitrate apart also because it's aqueous. Right, and we can see that on both sides of the equation we have these nitrate ions that aren't really doing anything. And so those are our spectator ions, and they're not going to take part in this reaction. So what we have here is we have copper in a 2+ oxidation state. And here we have elemental copper, so remember that means any element by itself has a 0 oxidation state. So we started with zinc by itself. So it originally had a 0 oxidation state, and then it went to the zinc cation with a 2+ oxidation state. So these are our two reactions. We have copper going from a 2+ to a 0, and zinc going from a 0 to a 2+. We have the number and type of atoms on both sides balanced, but now we have to balance the charge. So on this side of the arrow we have a +2 charge. Here we have a 0 charge. So we're going to add two -1 charges here, and those are our electrons. Here we have a 0 charge, here we have a +2, so we're going to add two -1 charges on this side, and those are our electrons there. Right? And so remember, the loss of electrons is oxidation, and the gain of electrons is reduction. So here copper is gaining electrons, so this is our reduction. And right, you can see this is being reduced from a 2 to a 0. And here zinc is actually losing electrons, so this is our oxidation. All right, so remember the difference between oxidation and reduction, and be able to point out which reaction is the oxidation reaction, which is the reduction reaction, and balance those two equations. Another skill you should have learned this semester, and unfortunately we didn't cover this in person, but you should be able to read a description of a chemical equation and then convert it to a chemical reaction and convert it to the actual chemical equation. So in this case we have barium carbonate powder is mixed with a solution of sulfuric acid. This produces barium sulfate precipitate, water, and carbon dioxide bubbles. So the problem here for a lot of people is you have to know your naming to be able to do this. So if you're having trouble with naming still, you need to brush up on your naming because you'll need to do some naming for the final exam. But first thing we want to do is look at this barium carbonate. So barium is element Ba. It's in group 2, so it'd form a +2 charge. If you go and look at your polyatomic ion table, you should have a carbonate on there with a -2 charge. Right, and so then we can see those are going to go together 1 to 1, a +2 and a -2, so we would have our barium carbonate. And here it says it's a powder, so that means it's a solid. So our state of matter would be solids. Remember your states of matter. And it's mixed with a solution of sulfuric acid. It tells you sulfuric acid is H2SO4. If it's a solution, that means it's aqueous. It's dissolved in water. So our products are barium sulfate. So if we look at our polyatomic ion table, sulfate is SO4, so SO4 2-, and Ba2+, those go together 1 to 1. Barium sulfate, and it says it's a precipitate, so that means it's a solid. The other thing formed is water, so you should know by now water is H2O. It's going to be a liquid and carbon dioxide bubbles. So this was a type 3 where the prefix tells us how many there are. So there's 1 carbon and 2 oxygen. And if it's a bubble, then it's probably a gas. The next thing you'd have to do is balance this equation. And here we have 1 barium, 1 barium, 1 carbon, 3 oxygen here, 4 there, so 7 oxygen on this side, 4, 5, 6, 7 on that side, so everything's balanced so far. We have 2 hydrogen. Here we have 2 hydrogen, those are balanced, and we already balanced our, we have 1 sulfur and 1 sulfur. So everything's balanced here, so this would be the balanced equation. You should also be able to do a calculation like this with using our mole map. Remember, if we have moles of something, we can always find grams, and the way to go from moles to grams is with the molar mass, which is the mass on the periodic table. To go from moles to atoms, we're going to use Avogadro's number, which is 6.022 times 10 to the 23rd. So we can freely convert all the way across there as much as we want. So let's look at this problem, calculate the number of copper atoms in 205 grams of copper. The first thing you usually want to do is kind of draw a little road map of where you're headed. So we know that we have grams of copper, all right, so we're going to start with grams of copper. If we're at grams, the only place we can go is moles, so we're going to go to moles of copper. And then where we're headed is we want to know the number of copper atoms, so we're going to go to atoms of copper, and that's the direction we're going. We're going just across this way on our mole map. So we're going to start with our 205 grams of copper, and we want to go to moles of copper, so we need to know how much 1 mole of copper weighs in grams, right? And to do that, we would look at our periodic table and get that mass off our periodic table. So if we kind of find copper on our periodic table, it's element number 29, and then its mass is 63.546. So that tells us that 1 mole of copper weighs 63.5, we'll just call it 63.55 grams. So you're going to find the element on the periodic table and take this mass. All right, so our grams of copper have canceled. We're at moles of copper. Now we need to go to atoms of copper, so we need to know how many atoms of copper are in 1 mole of copper, so we can cancel out our moles of copper, and that's just Avogadro's number, so this would be 6.022 times 10 to the 23 atoms of copper in every 1 mole of copper. So we take 205 divided by 63.5 and multiply it by 6.022 times 10 to the 23rd, and we should get a number like 1.94 times 10 to the 24 atoms of copper. So make sure you're able to move throughout the mole map. If you have moles, you should be able to get grams. If you have atoms, you should be able to get grams. You should be able to go anywhere across that mole map if you have moles of something or atoms of something.